Somewhere in the Powder River Basin right now, a locomotive that cost $3 million is hauling coal through Wyoming. It has been doing this for over 20 years, and nobody at the railroad has any intention of retiring it. The prime mover has been rebuilt. The traction motors have been swapped. The cab seats have been replaced twice. But the frame, the steel spine that holds everything together, is the same one that rolled off the assembly line before some of its crew were out of high school. And the reason it is still on the rails is the same reason every other aging locomotive in North America is still on the rails. Replacing it costs $3 million. Rebuilding it costs a fraction of that. The old machine still moves freight. That single economic fact has shaped the American railroad industry for the better part of half a century. What follows is the story of the $3 million locomotive, why railroads refuse to let it die, and what happens to a machine that was never designed to last this long. Pause for 1 second. A modern mainline freight locomotive weighs somewhere around 400,000 pounds. It carries a prime mover, a diesel engine roughly the size of a studio apartment that generates over 4,000 horsepower. That power does not drive the wheels directly. It spins a generator, which produces electricity, which feeds traction motors bolted to the axles. The locomotive is, in essence, a rolling power plant. The electronics alone would have been unrecognizable to a locomotive engineer 40 years ago. Microprocessors regulate fuel injection, monitor wheel slip hundreds of times per second, manage distributed power across a train that might stretch 2 miles, and report diagnostic data to a central office through satellite uplinks. The cab has screens. The engine has software updates. All of this costs money. A new mainline freight locomotive from either of the 2 remaining North American manufacturers runs somewhere in the neighborhood of $3 million, depending on configuration. Some configurations cost more. When a Class 1 railroad, one of the major freight carriers like Burlington Northern Santa Fe or Union Pacific, needs to refresh its fleet, the order is not for 1 unit. It is for dozens, sometimes hundreds. The capital outlay reaches into the hundreds of millions of dollars before a single wheel turns. That $3 million figure is not an outlier. It is the floor. Locomotives configured for heavy haul service with AC traction motors and the latest emissions compliance equipment can run higher, and the price has been climbing for decades, driven by the same forces that drive every other piece of industrial equipment: tighter regulations, more complex electronics, and fewer manufacturers competing for the orders. There used to be 3 major locomotive builders serving the North American market. Now there are 2. Competition still exists, but the pricing leverage has shifted. A railroad that does not like the quote from one manufacturer has exactly one alternative. That dynamic does not push prices downward. And here is where the economics get interesting. The locomotive that new unit is supposed to replace is still running. It is not running gracefully. It is loud. It drinks fuel. Its emissions would concern a regulator. But it moves trains. And moving trains is the only thing a railroad has ever cared about. Pause 1 second. If you want to understand why American railroads treat locomotives like they are immortal, you have to go back to 1972. That year, Electromotive Division, the locomotive building arm of General Motors, introduced a machine called the SD-42. It was not revolutionary. It was not the most powerful locomotive on the market. What it was reliable. The SD-42 ran on a 16-cylinder diesel engine designated the 645E3. EMD had been refining that engine family for years. It produced 3,000 horsepower, a respectable number for the era, and it did so without the chronic turbocharger failures that plagued some competitors. The electrical system was straightforward. The frame was heavy and simple. Nothing about the machine was exotic. Railroads loved it. Over the production run, which ran through the late 1980s, EMD built thousands of SD-42 units for North American railroads. Burlington Northern ordered them by the hundreds. So did Union Pacific, Southern Pacific, Conrail, and Norfolk and Western. The machine was everywhere, on every major corridor, in every kind of service. What nobody predicted was how long they would last. The SD-42 was engineered for a service life of perhaps 20 years. Some of them are still pulling freight more than 50 years after they left the LaGrange, Illinois, assembly plant. Not in museums, not on heritage excursion trains. In revenue service, hauling real tonnage for real money. The SD-42 taught the railroad industry a lesson it has never forgotten. A locomotive does not need to be the best machine available. It needs to be good enough, and it needs to be fixable. If a mechanic can rebuild the prime mover in a railroad shop with standard tooling and commonly available parts, the machine can run essentially forever. The original purchase price becomes irrelevant over a long enough timeline. What matters is the cost per mile over a service life that keeps extending year after year because nobody can find a reason compelling enough to stop. That lesson is the reason the $3 million locomotive exists today. Not because the new machines are $3 million worth of improvement, because the old ones, the machines that inherited everything the SD-42 proved, will not stop running long enough to justify the replacement. Pause 1 second. Locomotive economics are brutal in their simplicity. A railroad cares about one number above all others, the operating ratio. That is the percentage of revenue consumed by operating expenses. A ratio below 70% is excellent. Above 80 is trouble. Every decision about equipment, labor, and fuel filters through that number. A new locomotive improves the ratio in 2 ways. It burns less fuel per ton-mile, because newer engines are more thermally efficient. And it spends less time in the shop because its components are newer and its electronics can flag problems before they become failures. But those savings are not free. That $3 million purchase price sits on the balance sheet as a depreciating asset. The railroad has to finance it, insure it, and absorb the depreciation over decades. And the fuel savings, while genuine, take years to recoup the purchase price, especially when diesel prices run low. Now compare that to the alternative. The old locomotive is already paid for. Its depreciation hit the books long ago. A major overhaul, pulling the prime mover and rebuilding it from the crankshaft up, replacing traction motors, rewiring the control stand, costs somewhere between $500,000 and $1 million depending on the scope. That is a fraction of the new unit price, and a well-rebuilt locomotive can run for another 15 to 20 years. The arithmetic is not complicated. If rebuilding an old unit costs a third of what a new one costs and delivers 80% of the performance, the old unit wins. It wins so convincingly that some railroads have structured their entire fleet strategy around it. They buy new locomotives only when they absolutely must, when the fleet physically cannot handle the traffic volume, or when regulations leave no alternative. Consider the scale. A major Class 1 railroad might operate a fleet of several thousand locomotives. Even replacing 10% of that fleet in a single year would mean an order for hundreds of new units at $3 million each. That is a capital commitment that competes directly with track maintenance, signal upgrades, terminal expansion, and shareholder returns. The locomotive that is already running, already paid for, already earning revenue, has a powerful institutional ally, the capital budget. This is not sentiment. This is math. Pause for 1 second. The rebuild happens in vast, echoing shops that smell like diesel fuel and hot metal. Every major Class 1 railroad operates at least one heavy locomotive maintenance facility. Some are the size of aircraft hangars. A locomotive comes in under its own power. It rolls onto a designated track, and a crew of electricians, pipe fitters, machinists, and diesel mechanics begins taking it apart. The process can take weeks or months. The prime mover comes out first. Overhead cranes lift the engine, all 20 or 30 tons of it, straight up through the long hood and lower it onto a stand. From there it goes to the engine shop, where machinists disassemble it cylinder by cylinder. Liners are honed or replaced. Pistons and connecting rods are inspected, measured, and either reused or swapped for remanufactured components. The crankshaft is checked for trueness on a precision lathe. The turbocharger is rebuilt or replaced with a remanufactured unit. Every gasket, seal, and bearing is new. While the engine is out, the electrical crew strips the main generator and traction motors. Armatures are tested for shorts and grounds. Commutators are turned to specification. New carbon brushes are fitted. The entire control system, the contactors and relays and increasingly the circuit boards, gets bench tested and replaced as needed. The frame itself is inspected for cracks using magnetic particle or ultrasonic testing. The trucks, the wheeled assemblies beneath the locomotive, are rolled out and overhauled. Wheel treads are turned to profile. Bearings are pressed and replaced. Brake rigging is rebuilt. When everything goes back together, the locomotive is essentially new from the trucks up through the prime mover. The frame is original. The cab is original, though it usually gets new seats and sometimes a fresh control stand. The long hood sheet metal gets patched and painted, a fresh coat in the railroad's current livery, and the machine rolls out looking like it came from the factory. It did not. It came from 1998 or 1993 or sometimes earlier. But it will run like a new machine for a while, and then it will gradually wear again. And in another 15 years, it will come back to this same shop for the same process. The cycle continues until the frame cracks or the railroad can no longer source parts for the model. Historically, that takes a very long time. In the 1990s, both major North American locomotive manufacturers chased a new frontier. The goal was a single locomotive producing 6,000 horsepower, enough to replace two older 3,000 horsepower units on heavy-haul routes and cut crew costs dramatically. GE developed the AC6000CW. EMD built the SD90 Mac. Both were massive machines, among the heaviest and most powerful diesel-electric locomotives ever put into regular freight service. Both cost significantly more than the standard 4,000 horsepower models that were already selling well. And both had problems. The GE units experienced persistent issues with their new prime mover, an engine built specifically for the application by a European manufacturer. Early production units were delivered with a smaller interim engine, while the larger power plant was still being sorted out. Some railroads received locomotives that never got the engine they were originally promised. The EMD units had parallel struggles. The new 16-cylinder engine designed to deliver 6,000 horsepower proved difficult in service. Reliability fell short of the older, proven power plants. Some railroads found that the fuel savings from running one large unit instead of two smaller ones disappeared when the big machine spent too much time in the shop. Within a decade, the experiment was largely over. Both manufacturers retreated to the 4,000 to 4,400 horsepower range, where proven engine platforms delivered the dependability that railroads actually needed. Many of the 6,000 horsepower units were derated, rebuilt with smaller engines, or shifted to less demanding service. The machines they were supposed to replace, the older 4,000 horsepower units that cost less and broke down less often, kept running. The horsepower race confirmed what the SD42 had already proved a generation earlier. Railroads do not want the most powerful machine on the market. They want the one that starts every morning. Pause for 1 second. For decades, the decision to keep or retire a locomotive was purely economic. Then the Environmental Protection Agency changed the equation. Federal locomotive emission standards, organized into tiers, began tightening in the early 2000s. Tier 0 covered the oldest machines. Each subsequent tier demanded lower levels of nitrogen oxides, particulate matter, and other pollutants. The most recent standard, Tier 4, took effect for newly manufactured locomotives around 2015 and required dramatic reductions from earlier levels. Tier 4 compliance changed the locomotive fundamentally. Meeting the standard required exhaust after-treatment systems, selective catalytic reduction hardware, diesel particulate filters, and sophisticated engine management software to balance power against emissions. The engines became more complex. The locomotives became heavier because the after-treatment equipment takes up space and adds weight. Maintenance costs rose because the emission systems require their own service cycle. This created a paradox. The regulation designed to push older, dirtier locomotives off the rails actually gave railroads a financial incentive to keep them. A Tier 0 or Tier 1 locomotive that is rebuilt does not have to meet Tier 4 standards, because the federal rules treat it as a remanufactured unit, not a newly manufactured one. Remanufacturing standards are less stringent, so a railroad can rebuild a locomotive from the mid-1990s to a cleaner but not Tier 4 standard and keep running it legally. The result is a fleet that ages in place. The newest machines meet the strictest emissions requirements but cost more to buy and maintain. The oldest machines meet weaker standards but cost less to keep running. The railroad, caught between regulatory pressure and economic reality, keeps both, assigning the older units to routes and services where they attract the least regulatory attention. Some railroads have taken this further, operating dedicated rebuild programs that bring old locomotives up to improved emission standards without the full cost of Tier 4 compliance. The remanufactured unit burns cleaner than it did when it was new, but not as clean as a factory-fresh machine. It occupies a regulatory middle ground that satisfies the letter of the law while allowing the railroad to defer the $3 million purchase for another decade. Pause 1 second. The mandate that nearly killed the oldest locomotives was not about emissions. It was about safety. Positive train control, a federally required system designed to prevent collisions, overspeed derailments, and unauthorized entry into work zones, forced railroads to equip every locomotive operating on certain track classes with GPS receivers, onboard computers, and wireless communication hardware. The compliance deadline, extended several times by Congress, arrived in the early 2020s. New locomotives came from the factory with positive train control built in. Older ones needed a retrofit. Each unit required antennas, wiring runs, display screens in the cab, and a dedicated computer system that communicates constantly with wayside infrastructure and a back-office server. The installation took days per locomotive. Some railroads used the deadline as a natural retirement trigger. If a locomotive was old enough that the cost of the retrofit approached the remaining value of the machine, parking it made more sense than upgrading it. This culled the very oldest units from active fleets, machines from the 1970s and early 1980s that had survived every previous round of rationalization. But for locomotives that were merely middle-aged, 15 or 20 years old, the retrofit was just another cost of doing business. The railroad paid for the installation, certified the system, updated the software, and sent the machine back to work with a new antenna on its roof and a computer tucked between its frame rails. Technologies that did not exist when the locomotive was designed now rode along on every run, monitoring its position, its speed, and the track ahead. The positive train control mandate did something else, something the regulators may not have intended. By requiring every active locomotive to carry the system, it created a hard floor for the minimum investment a railroad was willing to make in any given unit. If the railroad was going to spend the money to install the electronics, it wanted to be sure the locomotive would run long enough to justify the cost. Marginal machines that might have been parked got rebuilt instead, because the PTC investment only made sense on a unit that would stay in service. The safety mandate, paradoxically, extended the lives of the machines it was installed on. Ask a locomotive engineer which machine they prefer, the new unit or the old one, and the answer depends on who you ask. The new locomotives have better cabs, climate control that works, seats with real suspension, electronic displays showing exactly what every system is doing. The ride is smoother because the trucks are built to tighter tolerances. On a 12-hour run across the plains in July, the new cab is a genuinely more comfortable workplace. But comfort is not everything in a locomotive cab. Predictability matters. The older machines, the ones engineers have been running for 2 decades, behave in ways that experienced crews understand on instinct. An older locomotive with conventional DC traction motors responds to the throttle in a way that feels mechanical and direct. Notch it up, the engine spools, the train moves. When something goes wrong, the engineer often knows what it is before the warning light comes on. because they have heard that particular knock or felt that shudder 100 times. The newer AC traction locomotives are more capable machines. They haul more tonnage up steeper grades because AC motors produce higher tractive effort at low speed without overheating. But they also have software between the engineer and the rail. The microprocessor decides how much power each motor receives, how aggressively to manage wheel slip, when to derate for thermal protection. The engineer gives the command. The computer interprets it. When that interpretation fails, when a software glitch forces an unexpected power reduction on a grade, the engineer has fewer options. You cannot troubleshoot code with a wrench. The older engineers, trained on SD42s and GP38s, tend to trust the mechanical simplicity of the old machines. The younger crews, raised on the new technology, often prefer the screens and the air conditioning. The railroad consults neither group when deciding what stays and what goes. When a Class 1 railroad finally declares a locomotive surplus, the machine is not dead. It is for sale. A sprawling secondary market exists for used freight locomotives. Short line and regional railroads, the small operators running branch lines and local freight on track, the Class 1s abandoned, buy surplus units by the dozens. A used SD42 or GP38-2, 30 years old and freshly stripped of its Class 1 paint, sells for a small fraction of what a new locomotive costs. For a short line generating modest revenue, that price is not just affordable. It is the only realistic option. Leasing companies play a role as well. Several firms specialize in acquiring surplus locomotives, overhauling them, and leasing them back to railroads that need extra power for seasonal surges, unit train contracts, or temporary replacements while their own units sit in the shop. These leasing fleets tilt heavily toward older models because the economics favor machines with low book value and proven mechanical simplicity. The international market absorbs units too. Railroads in Mexico, South America, and parts of Africa have operated retired American locomotives for decades. A machine that is too old and too dirty for North American emissions standards may face no such restriction in a country with different environmental regulations. The result is a locomotive with 3, 4, sometimes 5 careers, built for a Class 1 in the 1980s, rebuilt in the 1990s, sold to a regional in the 2000s, leased to a grain shuttle in the 2010s, exported to a mining operation in South America in the 2020s. At each stage, someone looked at the locomotive, looked at the price of a replacement, and reached the same conclusion. Keep it running. Every locomotive eventually reaches the end. When it does, the machine goes to a place that rail fans call the boneyard. Locomotive storage lines and scrapping facilities are scattered across the American West, often in desert locations where dry air slows corrosion. Rows of dead locomotives, sometimes hundreds of them, sit on weed-choked sidings with their number boards removed and their cab windows dark. Some machines sit in storage for years before anyone decides their fate. A railroad parks a surplus locomotive, drains the fluids, disconnects the batteries, and walks away. If traffic picks up, the unit can be reactivated, a process that takes days or weeks depending on how long it has been sitting. If traffic stays flat, the locomotive waits until the railroad sells it for scrap or finds a buyer. Scrapping is methodical. Specialized firms buy the machines at scrap value, which tracks the weight of the steel and the value of the copper in the electrical system. The wiring comes out first because copper is the most valuable component per pound. The prime mover is pulled and either resold as a remanufacturing core or cut apart with torches. The frame is sectioned and loaded onto rail cars for delivery to a steel mill, where it melts down into rebar, structural beams, or possibly the frame of a new locomotive. The trucks sometimes survive the process. If the wheels and axles are in serviceable condition, they get resold or placed into storage as spares. A wheel set from a locomotive scrapped in 2020 may end up beneath a locomotive built in 2005, running on a prime mover originally installed in a machine from 1994. The lineage becomes untraceable. What does not survive is the identity. The locomotive number, the 4 or 5-digit designation painted on the cab, is retired when the machine goes to scrap. The railroad may reassign that number to a new unit years later. The physical machine becomes raw steel again, and the designation carries on. In a way, the railroad ensures that nothing ever fully retires. It just changes form. Pause for 1 second. The locomotive sitting at the head of a freight train today is, in most cases, a compromise. It is not the newest machine available. It is not the cleanest, the most fuel-efficient, or the most technologically advanced. It is the machine the railroad already owns, rebuilt just enough to keep hauling, because the cost of replacing it with something better is $3 million that could go somewhere else. This is not a failure of the industry. It is the industry working exactly as designed. Railroads are not in the business of owning impressive machines. They are in the business of moving tonnage from origin to destination at the lowest possible cost per ton-mile. If an old locomotive accomplishes that, the old locomotive stays. The manufacturers understand this completely. They engineer new locomotives for 30-year service lives with modular components that can be swapped and rebuilt in the field. They offer long-term maintenance contracts that include scheduled overhauls at fixed prices. They build the machine knowing the railroad will extract every possible mile before placing the next order. And the locomotive itself, if it could register anything at all, would register only this: it is not going to retire. It will run until something fundamental fails. A frame crack, a structural fatigue event that makes rebuilding more expensive than replacement. And even then, its traction motors will scatter to a short line in the southeast, its trucks will roll under another machine, its cab instruments will sit in a collector's garage in Ohio. The $3 million question was never whether to retire the locomotive. It was always how long retirement could be postponed. That freight locomotive you glimpsed from the highway overpass this morning was probably built before the turn of the century. It has been rebuilt at least once, repainted at least twice, and assigned to its current route because the machine that would replace it costs $3 million. Its prime mover has outlived the engineers who broke it in. Its frame has crossed the continent more times than anyone has bothered to count. It is loud. It is old. And it will be back on this same track tomorrow.